So hi, good evening. Let's just wait. Yeah, good evening. Let's just wait for 2 minutes. If someone wants to join, and then we will begin. Okay. I think let's. Okay. So like this is the third week of the interactive session. So last week mainly we were discussing about temperature, pressure, and density with respect to height and atmosphere. So we and both pressure and density is exponentially decreasing with respect to height. And in case of temperature, we have divided the atmosphere into different layers. Has its own pattern of variation with respect to height. Like if in the troposphere there is a decrease with respect to height, whereas in the stratosphere there is an increase mainly because of the presence of ozone. And again in the mesosphere there is a decrease, and in the thermosphere we are able to see an increase in the temperature with respect to height. And we also learned about the electrical properties of the atmosphere, mainly the ionosphere, because of the solar wind and all high energy solar winds knock the electrons out of the molecules in the ionosphere, so they become charged ions. And how their properties, different layers in the ionosphere, how they are used for this um, radio communication, all these things we were discussing in the last class. So this class we will be mostly numericals because I think the NPTEL class whatever was week 3 has started with the classification of the derivation of those forces and all those things, and your assignments also mostly contains numerical problems. So this week mostly we will deal with a number of numerical problems related to your assignments. Okay, so just as a recap, as I told last class, we were learning this vertical variation of pressure and density with respect to height. So if you remember the equation, what was it? How did we represent the vertical variation of pressure and density with respect to height? In case of pressure, it was P is equal to P0 e raised to minus z by h. In case of density, it is rho is equal to rho 0 e raised to minus z by h, where P0 is the surface pressure, P is the pressure at the height z, and h is known as the scale height of the atmosphere. In case of pressure, it is basically the height at P becomes 1 by E times of the surface pressure, and in case of density, it is the height at which density of the atmosphere becomes 1 by E times of the surface density. So this is basically the equation. This is basically how pressure and density is varying with respect to height in the atmosphere. Both of them are showing an exponential decrease. That is, as we move up in the atmosphere, both pressure and density is showing a decrease. Now let's move on to a problem. So the problem is basically assume that an exponential, both pressure and density is having an exponential decrease with respect to height, and they have given the scale height as 7.5 millimeter. 7.5 kilometer, and the question has to estimate the density of the atmosphere at a height of 2 kilometer from the surface. So we have to estimate the density of the atmosphere, and what they have given, density of atmosphere as sea level and acceleration due to gravity. So what the things that are given, they have given the scale height of the atmosphere, which is capital H, which is given as 7.5 kilometer. They have given the height set at which we have to calculate the density. They have given the surface density, which is rho 0, 1.29 kilogram per meter cube. They have given the value of G as 9.8 meter per second square. Just a second, yeah. So this much things they have given. G is equal to 9.8 meter per second, and we have to calculate rho at a height of Z is equal to 2 km. Which equation should we use? Can you tell me? Which equation should we use? Yeah, rho is equal to rho 0 e raised to minus z by h. And we want to calculate rho. So do we know rho 0? What is rho 0? 1.29 into e raised to minus, what is the value of set? 2 kilometer by scale height is 7.5. Like we can convert it into meter because it is division, both it will cancel out basically. 2 kilometer will be 2 into 10 raised to 3 meter, and 7.5 kilometer will be 7.5 into 10 raised to 3 meter. So it will eventually cancel out. So you can just write 2 by 7.5, which will give you a value of, can you tell me, calculate and tell me. If you got the answer, you can put it in the chat box also. Did anyone got the answer? Two by 7.5. Yeah, correct. 1.29 into e raised to minus 0.26 will come. When you calculate, it will be 0.99 something will come, kilogram per meter cube, which is basically 1 kilogram per meter. So this will be the density of the atmosphere at a height of 2 kilometers. So what we did, we know how the density is decreasing with respect to height. The equation is basically rho is equal to rho 0 e raised to minus z by h, and h has been given, scale height is given, and we know at what height we need to calculate the density, which is basically 2 kilometer, and the surface density is also given, which is rho 0. So just substitute, and finally you will get around 0.99 kilogram per meter cube, or 1 kilogram per. So while traveling height of 2 kilometer, the density of the atmosphere decreases from 1.29 to 1 kilogram per meter. Okay, I hope you got the answer. It is a direct question, everything is given. Now let's move on to the second question. So the question is to given the mean pressure at Earth's surface as 985 hectopascal and radius of the Earth is 6,400 kilometer, the total mass of Earth's atmosphere is. So we have to calculate the total mass of Earth's atmosphere. The things that are given: surface pressure is given as 985 hectopascal. Then the radius of the Earth is given 6,400 kilometer. We have to calculate the mass of the Earth, and this equal to question. So basically, what is pressure? Can you tell me basic definition of pressure? Pressure is defined as the force per unit area. Pressure is basically F by A. So here we are considering the atmosphere, right? Suppose this is the Earth, this is the atmosphere. So this pressure is exerted by this much atmosphere on the surface. So the force exerted by the atmosphere at the surface is basically mg by A. Force exerted by the atmosphere is mass of the atmosphere into G, mg by A. So basic A will be the area of the Earth. So like atmosphere is an envelope surrounding the Earth. So like whole along this area, atmosphere is exerting this force on the surface of the Earth. So what will be the area of the Earth? How can we calculate? Area of the Earth or area of a sphere will be area of a sphere is given by area of the sphere is basically 4 pi r square. So r will be the radius of the Earth. So P is equal to mg by 4 pi r square. This is the equation. We want to calculate m. It will be P into 4 pi r square by g, which will be equal to P is 985 hectopascal into 4 pi into r is 6,400 into 10 raised to 3 kilometer. We have to convert it into meter. Whole square divided by g, which is 9.8. Can you calculate it and tell me? If you got the answer, you can put it in the chat box also. get I think some mistake is there. That will come around 5.17 into 10 raised to 18 kilogram. I don't know where did you go wrong. It's just okay? Yeah. Did anyone else got? I think this is the correct answer. Yeah. So what was the question? The question was to find the mass of the Earth's atmosphere, right? So the things that have been given was the surface pressure was given, which was 985 hectopascal, and also the radius of the Earth was given. The radius of the Earth was given as this distance was given as 6,400 kilometers, right? So we wanted to calculate the mass of the Earth. Pressure is given. So pressure is basically force per unit area. F by A is pressure. So in this case, the force is basically mg, that is the weight of the atmosphere which is exerted on the surface, divided by area. So the atmosphere is enveloping the whole Earth. So the area will be basically the area of the Earth only. So by 4 pi r square, which is basically the area of the 4 pi r sphere, 4 pi r square, and r is the radius of the Earth. So mg by 4 pi r square. We know pressure. We have to calculate m basically. So after rearranging, it will become m is equal to P into 4 pi r square by g. After substituting whatever values have been given, they will get an answer around 5.17 into 10 raised to 18 kg. Okay, I hope you got the answer. Now let's move on to another problem. So the problem basically says that the cruising altitudes of two commercial aircraft, basically A and B, are 15 kilometers and 25 kilometers respectively. If the scale height of the atmosphere is approximately 7.5 kilometers, calculate the relative difference in air density between these two altitudes. So basically there are two aircrafts. One is flying at a height of 15 kilometers and another is flying at a height of 25 kilometers. And they want to calculate the density of the air at these two heights. At 15 kilometer, what is the density of the air, and at 25 kilometer, what is the density of the air, and just to compare those two values. So we have height, we have scale height, we want to calculate density. Which equation we will use? Yeah, rho is equal to rho 0 e raised to minus z by h. That's exponential relation only. So two heights are there. Set A, let it be 15 kilometers, height at which aircraft A is flying. And there is set B, let it be at a height of 25 kilometers. Is the height at which the aircraft B is height at which aircraft B is flying. And then the scale height is given, h is equal to 7.5 kilometers. So we want to calculate rho A by rho B. Okay, so rho A will be equal to rho 0 e raised to minus 15 by h, right? And rho B will be equal to rho 0 e raised to minus 25 by right? So we want rho A by rho B, which will be basically rho 0 e raised to minus 15 by h by rho 0 e raised to minus 25 by h, which will become rho 0 and rho 0 will be gone, e raised to minus 15, and it will go up plus 25 by h, which is equal to e raised to minus 10 by h, which is basically 7.5 kilometers. How much it will be? So rho A will be around, did anyone get? E raised to minus 10 by 7.5, which is basically 0.26 rho B. Is it correct? Did anyone get? Yeah. Okay. Yeah, 0.26 rho B. So basically A is flying at a lower height compared to that of B, right? The density at the point B will be less basically. So that's why rho A point two, rho B into 0.26. So rho A is comparatively less than rho B. So rho is, yeah, rho B is smaller than rho A. Yeah, correct. Rho B is smaller than rho A. Rho A is higher than rho B. Yeah, because B is at a higher height. And Sanjana, I just saw your answer. Can you check the power actually? How much it will be? 5.0. I am talking about the previous question. 5.06 into 10 raised to. Is it coming as 10 raised to 18, right? You got the answer? Yeah. So just check the power, okay? Yeah, it is basically mass of the earth is coming as 5.17 into 10 raised to 18 kilogram. Just check the power ones. Okay. So yeah, so this was so this is how we find out the relative density basically. So the density of the air at height B is less than that of the density at height A because it is decreasing with respect to height. I hope this is clear. So yeah. So let's move on to forces basically. So I think the week 3 class was mostly based on forces, different types of forces and all those things. Then I think it went on in explaining each force, like deriving each force like that. So basically forces can be divided into, this is just a recap just to remind you. Yeah. So forces have been divided into two, surface and body force. So surface force basically acts on the boundary between two medium or two different surfaces. Suppose this is uh, one body and this is sorry, this is the surface. The force that is acting here is basically known as the Fs or F surface. It is independent of the mass of the body. Like frictional force is an example of surface force. It just acts on the surface of the boundary between two mediums. And then there is an yeah, friction, viscous, all these are example of surface forces. It basically act on the boundary between the two surfaces. And there is another force which is known as the body force. Body force acts on the center of mass of the object, and it is directly proportional to the mass of the body. And gravity is an example of surface force. Sorry, body force. Friction, viscous force, etc. are example of surface force. It is independent of the mass of the body, where in case body force acts on the center of mass of the object and is directly proportional to the mass of the body. Higher the mass of the object, higher will be the force, etc. So that an example is gravity. So these are two different forces. And there is another classification which is basically known as real force and apparent force. So this is basically based on the inertial frame of reference that we are considering. So real force acts on an inertial frame of reference, and apparent force is what is basically acting on a non-inertial frame of reference, that is an accelerated frame of reference. Apparent forces basically act on accelerated frame of reference or non-inertial frame of reference. And example of real forces are pressure gradient force, gravity, frictional force, etc. Example is pressure gradient force, gravity, frictional force, etc. Whereas the example of non-inertial or apparent or non-inertial forces are Coriolis, centrifugal, etc. So these come under apparent force and these come under real force. So based on the frame of reference, it have been divided into two, real force and apparent force. Real force is basically what is acting on an inertial frame of reference, and apparent force is what is acting on a non-inertial frame of reference. In case of real force, the examples are pressure gradient force, gravity, and frictional force, whereas apparent forces examples are Coriolis and centrifugal force. And another important thing that you would have studied is the pressure gradient force. So pressure gradient force is basically the force acting if there is just a pressure gradient. So basically in the atmosphere, the surface there is a high pressure. As we go up, there is a low pressure. So there is a tendency for the air parcels to move from high pressure to low pressure. So this force which is acting from high pressure to low pressure is known as the pressure gradient force. This is basically caused by the pressure gradient. Basically caused by the pressure gradient because of the difference in pressure between the it's stick in the atmosphere, if we can say. So if we are considering the atmosphere, at the surface there is a higher pressure and at height there is a lower pressure. So there is a force acting from high to low pressure. That is, the parcel has a tendency to move from high pressure region to low pressure region. This is gradient force. And pressure gradient, which is actually acting in an opposite direction. Force is acting from high pressure to low pressure, and the gradient is in the opposite direction. So the force is acting in a direction opposite to that of the gradient. So this is basically pressure gradient force. You would have derived the equation. Pressure gradient force is equal to minus 1 by rho del P. So this basically del P basically shows the rate of change of pressure. And 1 by rho is per unit mass. It is basically derived in the form of force acting per unit mass of the body. So it will come as 1 by rho del P. derivation is there in the NPTEL class, you can check that. So this is the pressure gradient force. Now let's see, and this thing also you would have learned, which is very much important when we are talking about atmospheric motion, atmosphere as such. So hydrostatic equation, that says basically dp by dz is equal to minus rho g. So this shows that if we consider vertical motions in here, I will show you that once. Okay, just give me a second. Okay, then. Yeah. So hydrostatic equation, I'll just say once, like just to recap what it is. It is very important when we are talking about. And in atmospheric motions, it is one equation that we use a lot of. We'll have to go through. So suppose this is our atmosphere and this is Earth. Doesn't look like, but still, just imagine. So this is our atmosphere. In the atmosphere, I said, in the atmosphere surface there is a high pressure, and as we go up there is a low pressure. So we have this high pressure to low pressure. There is a pressure gradient force acting on the atmosphere. So pressure gradient force is there, and so there is a upward acting pressure gradient force, which is given by uh, minus 1 by rho. So since we are considering vertical direction, this rate of change of pressure with respect to height. So it is dp by dz. Basically dp by dz will come. So it is acting in the upward direction. And then there is gravity or gravitational force is there, which is acting downward. So downward acting force will be mg. As I said, we are basically considering the forces acting per unit mass. Unit mass, if it is unit mass, it will just be g. Force, gravitation, or g force will be basically g. So hydrostatic equation or hydrostatic equilibrium basically says that the pressure gradient force acting on an air parcel is equal the downward acting gravitational force. These two forces are in equilibrium basically. So which means the pressure force is minus 1 by rho dp by dz is equal to downward acting gravitational force. So if these two forces are equal, then the atmosphere is said to be in hydrostatic equilibrium, and this equation is basically known as the hydrostatic equation. dp by dz is equal to minus rho g. This is the hydrostatic equation. So it basically shows that the pressure gradient force acting on an air parcel is equal to the downward acting gravitational force. So when the atmosphere follows this condition, it is basically called the atmosphere. Said the atmosphere is in hydrostatic equilibrium. and the equation is known as, this equation is known as hydrostatic equation. Okay, dP by dz is equal to minus rho g. This is a very important equation. So the next question is actually, suppose in an isothermal atmosphere with surface temperature T is equal to 288 Kelvin, what will be the pressure at, I haven't wrote the kilometer. Just let me check the question. Yeah, pressure at 2 kilometer from the surface. What will be the pressure at 2 kilometer from the surface? Let's say 2 kilometer. Okay, set this equal to 2 kilometer. So the question, in an isothermal atmosphere, you know what is meant by isotherm or isothermal? What does it mean by isothermal? Have you heard? Isotherms, isobars, something like this? Have any idea? Yeah. So isothermal basically means the temperature is, yeah, temperature is constant. So in an isothermal atmosphere, in the sense, assume that the temperature of the atmosphere is a constant. It is just an assumption, is not the real case, but we are assuming that the temperature is constant. And the temperature of the atmosphere is basically 288 Kelvin. So we are assuming the whole atmosphere is having a single temperature. So it is basically an isothermal atmosphere, and the temperature of the atmosphere is 288 Kelvin. We want to calculate the pressure at 2 kilometer, and what is given is P0, which is 1000 hectare pascal. So we want to calculate P. Okay. So which equation we will use? So we know this equation, we basically know is like P is equal to P0 e raised to minus Z by H. You know, this is how the pressure is varying in the atmosphere. But in this case, one component is missing, which is H. The question is not providing the value of H. Instead, it has told the atmosphere is isothermal, and they have given the temperature of the atmosphere. So with these two conditions or assumptions, we have to find the pressure at P. So with the help of hydrostatic equation and equation of state, or ideal gas equation, we can actually solve this problem. Okay. So do you guys remember? So we know what is hydrostatic equation. dz is EP by dz is equal to minus rho g. We just learned that, right? And what is the ideal gas equation? You remember? Plus 2 physics. Ideal gas equation. Yeah. Ideal gas equation is PV is equal to nRT. So this equation is basically represented in terms of moles. For n moles of gas, this is the equation. Now let's just convert it in terms of mass. Mass of the air parcel, mass of the air. In atmosphere, when we are doing problems, we generally prefer mass instead of number of moles or those things. So generally in problems, we will be getting the mass of the air parcel, mass of the atmosphere. Basically, I have been using this term air parcel for a long time. So air parcel means in the atmosphere, we are just taking a small portion which is having a very small volume, an infinitesimal volume. From the atmosphere, I am just taking a small portion which is having an infinitesimal volume of air. So this thing is basically called as an air parcel. So when we talk about problems, motions and everything, this is one terminology that we generally use, air parcel. So PV is equal to nRT is the ideal gas equation. So basically rho is equal to mass by volume. So here we can write P is equal to, suppose number of moles is 1, RT by V, and we are considering unit mass of parcel, or the mass of the parcel is basically 1 unit. So this can be written as P is equal to rho R T. So M by V is equal to rho R T. So V we can substitute as M by V is basically M by rho. So if M we are considering it as unity, V will become 1 by rho. Substituting in PV is equal to nRT, we will get P is equal to rho RT. I think it is clear. So dP by dz is equal to minus rho g and P is equal to rho RT. These are the two equations that we have. I think it is becoming too much crowded. Yeah. So what we did, we know what is the, we just learned the hydrostatic equation, and then we know what is the, from the basically the equation of state or ideal gas equation that you have learned in your plus 2, which is PV is equal to RT. We have PV is equal to RT. We have just modified the how it is represented. PV is equal to nRT, you all know. So from this, V is mass by rho is basically mass by volume. So V will be mass by rho. So V will become, so if we are considering unit mass, then V will become 1 by rho. Then we are substituting this in the ideal gas equation. So we'll get P is equal to rho R T. So we have two equations. dP by dz is equal to minus rho g, pressure gradient equation. Then P is equal to rho R T. From this we can substitute rho. Rho is equal to P by R T. If we substitute it in equation 1, we will get dP by dz is equal to P by RT into G. We will just rearrange it. We will get dP by P is equal to G by RT into D set. Got till here? So it's clear. So what we did, we are considering two equations basically. First one is the hydrostatic equation, dP by dz is equal to minus rho g, and second one is the equation ideal gas equation. So dP by dz is equal to minus rho g and P is equal to PV is equal to nRT. From PV is equal to nRT, we wrote V rho is equal to M by V and P is equal to M by rho. We are considering unit mass of an air parcel, so V will basically become 1 by rho. So after substituting, it gave P is equal to rho R. So we have these two equations. So with these two equations, dP by dz is equal to minus rho g and P is equal to rho RT. we rearrange the P is equal to rho RT equation to rho is equal to P by RT and substituted this in the in the hydrostatic equation. So we got dP by dZ is equal to P by RT into G. Rearranging it, we got dP by P is equal to G by RT dZ. Now we are integrating this equation. Suppose from surface pressure P0 to P, dP by P is equal to G integral 0 to Z G by RT into dZ. Okay, so from inside the integral, we can take G as a constant. We can take G out by R as universal gas constant. R also we can take out. And in this case, initially we told that the temperature of the atmosphere is also a constant. It is not changing with respect to height. That is the assumption that we made. So T also we can take outside. So G by RT integral 0 to Z dZ it will become. And this one dP by P will become log of P by P0. Integral dP by P is log P basically. So log P by P0 is equal to G by RT into Z. Right? Which implies P is equal to P by P0 is equal to, if we take log to this side, e raised to minus G by RT into Z. Okay, I think I missed a minus somewhere. Yeah, equation from the hydrostatic equation there is a minus sign. So dP by P is equal to minus G by RT. It is minus. So this minus will come. So P by P0 is equal to P0. P by P0 is equal to e raised to minus G by RT into Z. So it's just basically P is equal to P0 e raised to minus GZ by RT. So this was the equation that we have been using so long. That's just basically P is equal to P0 e raised to minus Z by H, where H is equal to RT by G. So this is how we find scale height basically in an isothermal atmosphere. So we derived the equation that we have been using, how the pressure is changing with respect to height. P by P0 e raised to minus GZ by RT. So from hydrostatic equation and the ideal gas equation, we derived the equation of equation for the exponential decrease of pressure with respect to height. So now we know how to calculate H with the value of T, right? So now H can be calculated as R T by G. So H will be basically, what is the value of R? R is universal gas constant. What is the value? The value of R is 287 Kelvin, Joule per Kelvin per kilogram. Sorry, R is equal to 287 Joule per Kelvin per kilogram. Okay, so this is basically in terms of mass. If we are considering this value will come, I think the value of R that we would have studied in plus 2 will be 8.314. So in this case, we are it is mole inverse, Joule mole inverse, kilogram inverse. It is basically. In this case, when we calculate it, when we are doing in with respect to mass, the value is 287. So we can calculate the value of scale height. H will be 287 into the temperature they have given. What is the temperature? Temperature they have given us 288 Kelvin divided by G. Can you tell me what is the value of H? 7.5 kilometer. That's what you are getting. Did anyone else got the answer? Yeah, yeah. Thanks. Yeah. So not kilometers. What will be the unit? 8434 is correct. What will be the unit? 8434 unit will be so it is base SI unit will come basically. What is the SI unit for distance? It will be meter. It is height, no? 8 point, yeah, meter. Yeah, 8.4 kilometer it will become. Answer is correct. The unit, yeah. Hmm. So it will be 8.4 kilometer basically. Scale height we got. Now we can calculate P, right? We have the ultimate aim was to calculate the value of P. We didn't know the value of H, so we derived the value. We derived what is the formula for H, and just we calculated the value for H. Now we have to find the value of P. P is equal to P0 e raised to minus Z by H. P0 has been given, which is 1000 hectopascal into e raised to Z is 2 by H we calculated as 8.4. Calculate it and tell me the value. What will be the value of P? Yeah. How much? How much? Yeah. 788, 794. Okay. Yeah, it will come around 780, 790, something like that. This much hectopascal, it will basically come. 1000 hectopascal. Yeah. Can you mute yourself? Actually, sound is coming. Someone's mic is on. Yeah, thanks. Okay. So what was the question? The question was to find the pressure at a height 2 kilometer if the temperature is given, considering it is an isothermal atmosphere. So this was the question. So the things that have been given was temperature is given, which is 288 Kelvin. Height at which we have to compute the pressure, it is 2 kilometer, and the surface pressure is also given, which is 1000 hectopascal. So we know that the atmospheric pressure is having an exponential decrease with respect to height. That is P is equal to P0 e raised to minus Z by H, where H is the scale height of the atmosphere. So in the previous equations, what are we have been doing? The value of H was given. So we just directly use the equation and use the value in the equation and we did the calculations. But in this case, they haven't given the value of H. But instead, uh, they have given 2 or 3 assumptions, such as basically the atmosphere is isothermal. That is, we are assuming the temperature of the atmosphere is not changing, and they have given the temperature of the surface temperature, which is 288 Kelvin. So we have T basically. The value of T was given. So now we have to find the value of P at a height of Z. So what we did, we derived this equation basically, which is P is equal to P0 e raised to minus Z by H. So for that we used the hydrostatic equation. The derivation you would have learned in the previous NPTEL, week 3 NPTEL class, the derivation is there, you can go through it. So the equation is basically dP by dZ is equal to minus rho G. This is the hydrostatic equation. So this is one equation that we used, and we also used the equation of state or the ideal gas equation, which is equal to PV is equal to nRT. When we are when you are writing in terms of density, it is P is equal to rho RT. So dP by dZ is equal to minus rho G, the the hydrostatic equation, and P is equal to rho RT, the ideal gas equation. These two equations were used. So with this, what we did was uh, we substituted the value of rho in hydrostatic equation as P by RT. So rho was found to be P by RT from the ideal gas equation. So we substituted it in the hydrostatic equation, and we got dP by P is equal to minus G by RT into dZ. And then we integrated it from surface pressure height Z, and uh, like height from 0 to Z. So after integrating, we got P is equal to P0 e raised to minus GZ by RT. So from this, it was found that H is basically RT by G. When we compared this with the equation that we have been using, that P is equal to P0 e raised to minus Z by H, it was found that H is basically RT by G. And this equation is applicable only if the atmosphere is isothermal. Okay, because in this case we are assuming that atmosphere is isothermal. So this equation P is equal to P0 e raised to minus Z by H can only be used if the atmosphere is isothermal, or if we are considering an isothermal atmosphere, then only this equation can be used. Okay. So from this we calculated the value of H. We know R is basically 287. If we are writing in terms of kilogram, it is 287. You'd 8.314 would be the value that you will be remembering. So in that case, we are writing with respect to number of moles of gas. Here we are considering 1 kilogram of the gas. So that's why the value changes to 287. So R value we know, which is 287. T has been given, which is 288. And G is also acceleration due to gravity. So we substituted it and we got a value of 8434 meter or 8.4 kilometer. And after substituting the value of H in this equation, we got the pressure to be 794, 780, whatever it is, we just calculate and write the value. So that much pressure we got. So this is the pressure of the atmosphere at a height 2 kilometers. I think it is clear. So as I said in the earlier case, or we know that the equation that we have been using, that is P is equal to P0 e raised to minus Z by H, was derived based on the assumption that we are having an isothermal atmosphere. By making the assumption that we are having an isothermal atmosphere, we derived this equation. So now let's consider the case when the atmosphere is not isothermal. It is more of a real case. So the atmosphere is not an isothermal atmosphere, but the atmosphere's temperature is decreasing linearly with height at 6.5 degrees Celsius per kilometer. So what is given is basically dT by dZ, or the lapse rate, 6.5 degrees Celsius per kilometer. If you remember, we have we have calculated this value in the last class. So dT by dZ, or the rate of decrease of temperature with respect to height, is given as minus 6.5 degrees Celsius per kilometer, and surface temperature is given as 288 Kelvin. Again, we want to find the pressure at a height of 2 kilometer and P0 is equal to 1000 hectare pascal. So in this case, the temperature is decreasing at a rate of 6.5 degrees Celsius per kilometer. So if the surface the temperature is T0 at a height of 2 kilometer, at T set the temperature of the atmosphere will be surface temperature minus gamma into Z. Gamma is basically the lapse rate or dt by dz, which will be basically 288 minus 6.5 into 2. How much it will be? Temperature of the atmosphere at height Z or at height 2 will be how much it will be? Yeah, it will be 275 Kelvin. So at a height of 2 kilometer, the height of the atmosphere is said to be or given to be 275 Kelvin. Now in this case, how can we calculate the pressure at the height set? So the equation for it is basically P, which is the pressure at height set, is equal to P0 into T0 minus gamma set, which is basically Tz by T0 into G by R into gamma. So gamma is the lapse rate. I think all other quantities you know. R is the gas constant. Other quantities have been given. So basically P will become P0 is 1000 hectopascal. So this is basically the equation if the atmosphere is not isothermal. We are considering the change of temperature with respect to height. So in that case, this will be the pressure, change of pressure with respect to height. So P0 is 1000, T0 minus gamma set we just calculated. It was 275 by surface pressure is basically 288 raised to G is 9.8 by 287 into 6.5. Can you calculate and tell me the value? I hope it is clear. So the equation when we are considering not an isothermal atmosphere. Suppose the temperature is, which is actually close to the real situation. In actual atmosphere is not isothermal. We know that the temperature is different layers are having different vertical profile of temperature. So in the initial height or initial 10 or 11 kilometer, it is having a lapse rate of 6.5 degrees Celsius per kilometer. So we are considering that real case. So in that case, the equation will become P is equal to P0 into T0 minus gamma set, or basically height temperature at the height set T set by T0 raised to G by R gamma, where gamma is the lapse rate of the atmosphere, R is the gas constant. Just calculate and tell me the value. Mm. 1000 hectopascal is the surface pressure. You got the same. You got the same answer. At a height 2 kilometer, again it is 1000 hectopascal. Ridhima, what is the unit of the value that you have provided? 1.44 what? What is the unit? Okay. So this is the final answer that you got, I guess. You guys try to work it out. So it will become basically 1000 into 275 by 288 will be, yeah, 2, sorry, 275 by 288, right? Yeah, it will be basically 0.954 raised to, if we work it out, 9.8 divided by 287 into 6.5. It will come as 5.25 into 10 raised to minus 3, right? Yeah. So 0.954 raised to 5.25 into 10 raised to minus 3. This will come as 0.999. Triple nine. Okay. Okay. I'm getting an answer of around 990 hectopascal. 99. Okay. Okay, fine. Yeah. Okay, almost close one. Okay, maybe I'm doing some mistake. Okay. 999 it is coming. 999, right? Okay. 999 hectopascal it is coming. Okay. Yeah. Yeah, because we have traveled only 2 kilometer of height. Yeah. That's it. Just 2 kilometers are like almost close to the surface only. Yeah. 0.25 hectare. Yeah. 0.25 hectopascal only. That much only changes coming. Okay. 95. I think you have got the answer. So it is having a change of distance, I guess. So when we are the same thing we have done earlier also. So when we are considering an isothermal atmosphere, it was coming around 794 hectopascal. And when at a height of 2 kilometer, again when we did, it is coming close to the surface pressure only, like 999 hectopascal. So there is not much change in the surface pressure when we are like when we are considering the real case basically. So this was like an ideal case when the atmosphere was isothermal, and here this is more close to the what do you say, more close to the actual situation. So in this case, it is at just 2 kilometer height from the surface. It is just close to it. There is not much change in the atmospheric pressure. It is close to 1000 hectopascals. So I hope it is clear. So just remember this equation. So if the atmosphere is not isothermal, then we are considering the actual case. If we are considering the temperature change also with respect to height, then the equation turns out to be P is equal to P0 into T0 minus gamma set by T0 the whole raised to G by R gamma, where gamma is the lapse rate of the temperature. Temperature lapse rate is given by gamma, and I think other variables you have familiar with. So this is when that we are considering the rate of decrease of temperature also with respect to height. So that is about pressure, density, all these things. How the pressure is changing, how the density is changing. I think we have done a lot of numericals now. I hope things are clear to you. Now let's move on. So we talked about pressure gradient force also, which is basically due to the change of pressure in the atmosphere. So in the atmosphere, basically that force is there for the air parcel to move from high pressure to low pressure. So that force which is basically happening. So if the pressure was same everywhere, then the atmosphere would have been stable. There won't be any movement. Because this pressure difference is there, this atmospheric motions are happening. So in the surface also, the wind always tries to travel. Wind always moves from a high pressure region to a low pressure region. If we consider the global wind systems and all these things, we can see this pattern generally. The movement will always be from a high pressure region to a low pressure region. So that is basically known as the pressure gradient force, which is very much important wind air movement in the atmosphere, or wind circulation and everything. So another important force is the gravitational and also the hydrostatic equation, which you should remember the equation. It is dp by dz is equal to minus rho g, which is a very much important equation that you will have to you will use the equation very often in atmospheric physics. So that is a very important equation, and the atmosphere is generally said to be in hydrostatic equilibrium. That is, we consider that the pressure gradient force and the gravitational force that is acting above the atmosphere is always in equilibrium. These two forces are always equal. That is said to be hydrostatic equilibrium. These two, so that equation is very much important. Hydrostatic equation is very much important. Okay, so that's about pressure, density, and all those things. Now we will move on to another force which is important, which is basically the gravitational force. I think we all know what is gravitational force. So basically, in the earth, two objects which are having a mass are mutually attract each other. So this is earth, this having a mass m. If there is another body which is having a mass small m, there is a force acting on this, which is basically the gravitational force. So gravitational force is given by Gm m by r square. So m is in the surface, this body is in the surface, earth surface. R is the radius. So this is what is basically gravitational force. So as I said, most of the cases we are considering per unit mass, right? So Fg, if we write per unit mass, it will become Gm by r, which is basically the gravitational force or acceleration due to gravity. F force by mass is basically acceleration. G is equal to Gm by r square. This is the acceleration due to gravity. We all know this, we are familiar with this things. And the value is basically 9.8 meter per second square. And we know, so this is what is happening if the object is in the surface. Suppose if we are considering our atmosphere, the parcel is at a height h. So this is the parcel, air parcel. So it is at a height of h. So this is r, this is h. This is the total distance between these two objects. So basically, G star, which is the acceleration to gravity at height h, will become Gm by r plus h the whole square, which can be written as Gm by r square into 1 plus h square plus h by r the whole square. This r square is not there. Yeah, 1 by h plus r the whole square, which again can be reduced into the form Gn by r square into 1 minus 2h by r, which is basically G into 1 minus 2h by r. Gm by r square is the acceleration due to gravity at the surface, right? So G into 1 minus 2h by r. This is the equation. Acceleration due to gravity at a height h is given by G star h is equal to G into 1 minus r. r. Okay, so what we did? So we know what is the force, gravitational force, which is Gmm by r square. And if we are considering unit mass, then F force by m, which is acceleration. In the case of this is acceleration due to gravity. So G will become Gm by r square. So G is equal to Gm by r square is equal to 9.8 meter per second square. So this is the case when the object that we are considering is at the surface of the earth. Since we are dealing with atmosphere, let us consider an object which is at a height h of the atmosphere. So the total distance becomes r plus h. So the equation reduces to, or it will change to, the acceleration due to gravity at height h is given by Gm by r plus h the whole square. And again reducing it further, we will get Gh star is equal to G into 1 minus 2h by r. So now let us calculate the acceleration due to gravity at the stratopause. Okay, acceleration due to gravity at the stratopause. What height is the stratopause, you remember? Stratopause is basically the boundary between 47. So let us consider it as 50 kilometers just for the ease of calculation. So at h is equal to 50 kilometer, what will be Gh star, or Gh what it will be? So it will become G into 1 minus 2 into 50 into 10 raised to 3 by, what is the radius of the earth? You guys remember? Radius of the earth is, yeah, 6,400 into 10 raised to 3, which will become, if we reduce this, will become 10 by 640 basically. So G into 1 minus 10 by 640. So this will become G into 1 minus 0.015. 0.985 it will come. So 9.8 into 0.985 will be, how much it is coming? Yeah, 9.65 meter per second square. So the acceleration due to gravity at the stratopause is coming as 9.65 meter per second square. So we know the acceleration due to, I'm writing here, okay, I don't have space there. So the acceleration due to gravity at the surface is 9.8, right? And now we got at the stratopause is 9.65. So if we want to quantify how much percentage change is there actually in the acceleration due to gravity. So basically 9.8 minus 9.65, 9.8, 9.8 into 100, right? So the question is what percentage change occurs in the acceleration due to gravity at the stratopause, right? Yeah, 0.0015 after converting it into percentage. I think it will come around 1.5%. Is it? You have to multiply by 100. If we are talking in terms of percentage, it is basically. Is it correct? 1.5%. Did anyone got? So 9.8 minus 9.65. You come around 0.15 divided by 9.8. It is 0.015. Then once we multiply it with 100, 1.5%. Yeah. So only this much changes there as we go up to the stratopause, right? From 9.8 to 9.65. Only 1% or 1.5 percentage is changing acceleration due to gravity. So generally, when we are considering atmospheric motions, or if the air parcel is moving from surface to a particular height, we generally consider that the acceleration due to gravity is constant because the change is very less. That's what we have seen now. So if this is for 50 kilometers. So when we are talking about atmospheric motions, it will be mostly occurring within the troposphere actually. So 10 kilometer, 8 kilometer, that much height only. So the change in acceleration due to gravity will be like more less. So that's why when we are talking about atmospheric motion or vertical ascent of parcels, we generally keep the acceleration due to gravity constant. Like this variation with respect to height is not considered when we are considering the atmospheric motion. So yeah, so this is how you calculate the acceleration due to gravity at a particular height. If you want to see a considerable change in the acceleration due to gravity, the height that we are talking about should be closer to the radius of the Earth. Like the radius of the Earth is 6,400 kilometer, right? And when we are talking about the atmosphere, it will hardly be 80 kilometer or something. So this radius of the Earth is very much higher compared to the atmospheric height. So if we want to see a significant change in the acceleration due to gravity, the height that the object is moving also should be comparable to the radius of the Earth. So when we are talking about satellite motions and all those things, or objects that are very far away from the atmosphere, then this variation of acceleration due to gravity comes into play. In the atmosphere, generally we keep it as constant because the variation is very small. I hope you got it. So now let's see another interesting aspect, which is the angular velocity of the Earth. So you know, like when we are considering our Earth is moving, it is revolving around the sun. At the same time, it is rotating along its own axis, right? This is the axis the Earth is rotating. Do you know which direction Earth is rotating? Like from which side to? Yeah. The Earth is basically rotating from west to east. The rotation of the Earth in its own axis is from west to east. So like this, the Earth is rotating always. So since it is having a rotating motion, or since it is rotating along its own axis, it should have an angular velocity. So the angular velocity is basically, in case of Earth, it is denoted as omega. Omega is given by 2 pi, is basically that distance that it covers as it completes one rotation, 360 degree or 2 pi, divided by the time that it takes to complete this rotation. So how much time the Earth takes to complete one rotation? 24 hours. So if we are talking in SI unit, it will be in seconds. So it will be basically 24 into 60 minute into 60 seconds. How much it will be? Can you calculate and tell me? Angular velocity of the Earth. Yeah. No, no. Total, that is basically the time in seconds, right? 24 hours equal to 84,600 seconds. What will be the angular velocity? Okay. So this one is basically we are calculating in radian per second. Okay. So, so I think, yeah, yeah, 7.2 into 10 raised to minus 5 radian per second. So when we are calculating it in radian per second, it will come as 7.2 into 10 raised to minus 5 radians per second. So this is the angular velocity of Earth. So now let me ask you a question. Suppose the radius of the Earth is increased from r to 2r. What will be the angular velocity of Earth? So we just calculated the, sorry, it will be unchanged. Yeah, exactly. Because the angular velocity is independent of the radius of the planet, right? In the equation, it only depends upon the time period it takes to complete one rotation. That it only depends on the time. There is no r component here. So basically, if we change the radius of the planet or radius of Earth, this is not going to change. So in case of Earth, we got it like this. Suppose for other, I'm just telling an hypothetical case. Suppose for another planet, it completes the one rotation in 5 hours or something. Then what will be the angular velocity? It only takes 5 hours to complete one rotation. Then what will be the angular velocity? 2 pi by, yeah, 5 into 60 into 60. Then will come around some radians. You do the calculations. So basically what I meant to say was the angular velocity doesn't depend upon the radius of the planet or radius of the object that we are considering. It only depends on the time period that it takes to complete the rotation, basically. Radian per second, right? Okay, okay, thanks. So that is, so this was just a hypothetical case. Just wanted to show you that the how it is depending upon the time period. So yeah, so yeah, that's it. I hope things are clear. So today we were talking about we did some numericals concerning the change of pressure and density with respect to height. And we learned that the equation that P is equal to P0 minus Z by H in case of pressure is uh, based on the assumption that the atmosphere is constant along the atmosphere, that we are considering the atmosphere is having same temperature throughout. The temperature is not changing with respect to height. And we found the which one? Which one? Which one? This one. Huh? Uh, yeah, yeah, huh? No, no, no. We are consider initially we are assuming that only 1 mole of like we are considering just 1 mole of a gas. So this yeah, RT. Yeah. Then volume is based. So if we are considering like N is equal to 1 mole, it will become PV is equal to RT, right? Then yeah, mass is equal to yeah, density is equal to mass by volume. Then again we are taking M is equal to 1. So rho will become 1. Yeah. So P is equal to yeah. Unit mass. Yeah. Mm, that we are considering. Yeah. So, so yeah. So in case of isothermal, we calculated the pressure at a height of 2 kilometer. And then again, if we are considering a more realistic case that the temperature is decreasing with respect to height, then the equation turns out to be P is equal to P0 into T0 minus gamma set by T0 raised to G by R gamma. And in this case, we again calculated the pressure at a height of 2 kilometer, and it was found to be close to the surface pressure, around 999 hectopascal only. And then we were talking about gravitational force. We found the acceleration due to equation for the acceleration of gravity, acceleration due to gravity with respect to height. So we got GH is equal to G into 1 minus 2h by R, and we calculated the acceleration due to gravity at the stratopores of the atmosphere, and we learned that the variation is very small. So generally in the atmosphere we calculate the we consider that the acceleration due to gravity is constant with respect to height. We doesn't consider this variation with respect to height because the variation is very much small. And then we talked about the angular velocity. So angular velocity is basically distance that it covers divided by the time it takes. So 2 pi is one rotation basically divided by time. So in case of Earth is 24 hours, we got the angular velocity as 7.2 into 10 raised to minus 5 radian per second. And it doesn't depend on the radius of the object or radius of the planet. Okay, so yeah, that's what we were talking about. Now let's see some atmospheric variable conventions. You know, how in the atmosphere these motions are, how we are defining these motions, what are the notations that we use for that, and all those things. Okay. Yeah. Yeah. Mm-hmm. Yeah. Uh-huh. No, no. Time period will change actually. Like based on the, I think time period of oscillation is actually dependent on radius, right? Yeah. Yeah. What the, yeah, time period of rotation. Yeah. No, 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 no. That I didn't say actually. No, no. Time can be different. Yeah. Okay. Yeah. You're right. So I was just meaning to tell like if the time period of oscillation is remaining the same, like if we are considering yeah, if we are considering two objects, Maybe they are having different radiuses, but then both of them are having a time period of oscillation that is same. In that case, sorry, time period of rotation. Sorry, time period of rotation. So if we had the time period of rotation is same, then the angular velocity will basically be same. But like the time period of rotation is in turn dependent on the radius of the object. Yeah, you are right. So we cannot like conclude that the angular velocity is independent of radius of object. Yeah. Sorry about that. Yeah, you are right. So we cannot conclude like that. So I was just telling based on this equation of the uh, if two objects are having different radiuses, but still the time period of rotation is same, then the angular velocity will also be same. Okay, I'm sorry about that. So since the time period of rotation is in turn dependent on the radius of the object, we cannot conclude like the angular velocity is independent of the radius of the object. So thank you for pointing that out. Isothermal equation. Isothermal equation is P is equal to P0 e raised to minus Z by H. Yeah. P is equal to rho RT. Okay. So basically you know that the density is okay. Density plus mass by volume. Is rho is equal to m by v. So if we are considering a unit mass of object or unit mass of air parcel, suppose m is equal to 1 kilogram, then rho becomes, yeah, 1 by v. Yeah. So generally we represent most of the equations with respect to unit mass, unit volume kind of thing. So that's why it turns like just to simplify the equation. So we will get finally we will get P is equal to rho RT. I think it is clear. Yeah. So yeah. I just wanted to talk about some conventions in the atmosphere, like different components of velocity and all those things. So generally, we have like three directions we will be having motions, like in the x, y, and z direction basically. Suppose this is z. So if we are considering a xy plane initially, this is north, this is south, this is east, and this is west. Okay. So this water motions are happening in the north-south direction. Like suppose we are considering the Earth like this, we have different latitudes, and then we have different longitudes, right? Suppose we are moving along the longitude. We are moving along the longitude. It is basically called meridional. The movement is basically meridional, like north to south movement. This direction movement is basically known as meridional. So if some wind is blowing along this direction, it is known as a meridional bend. And this component, when we are considering atmospheric motions, is the meridional component of that parameter, whatever we are considering. This movement along the longitude, along a particular longitude, is known as a meridional movement, which is basically in the y direction of j. In vector, it is represented as j. So the motions from in the direction of this north south to north is basically positive j, and the direction north to south is considered as minus j. So if the movement is from north to south, it is assumed to be negative meridional direction, and if it is from south to north, it is considered as positive meridional direction. positive z. And then if we are considering a motion in the east to west or west to east, that is along latitudes, like this, that is known as zonal motion. And in case of wind, the wind is known as zonal wind. This component is basically zonal component. It is represented by the letter I. So here, west to east motions are known as zonal motion. It is represented as I in the vector form. So if the motion is from west, it is positive, and if it is from east to west, it is minus I. Okay. I and minus I. So this along the latitude is known as zonal movement. Along the longitude is known as meridional movement. So if we are moving in the zonal direction, the change is actually coming in the longitude, right? Like we are moving in this direction and the longitudes are changing. So the change is basically delta y. And if we are moving in the meridional direction, the changes are happening in the latitudes, right? Like from this point to this point, the latitude is basically changing. So it is delta x. Okay. And in the atmosphere, the movement, like this is the earth, this is the surface, upward we are moving along z. This is altitudinal changes, vertical motion. So upward movement is positive k and downward movement is minus k. So basically zonal means we are moving along a latitude, along a particular latitude, the zonal movement, and it is represented by I. The changes are coming, like longitude will change as we are moving along this direction, and meridional means we are moving along a longitude, if we are moving, it is basically known as a meridional movement or meridional component. It is having north to south movement is basically meridional, and east to west or west to east is zonal. And then vertical motion, basically altitude. And when we are moving along a latitude, there is longitudinal variation. The longitude is actually changing. And when we are moving along a longitude, there is latitudinal changes. Here the altitude is changed basically in vertical motion. Now when we are talking about velocity, the zonal velocity or east to west velocity is basically known as u. When we are considering u, the changes are basically in the x direction or dx. This longitudes are changing. When we are moving along the x direction, longitudes are changing. The movement is known as zonal. In terms of velocity, it is represented as v. And when we are moving in the meridional direction, changes are in velocity is represented as v, changes are dy or latitude. And the vertical motions called as w. movement is along the z direction. Altitude itself changes. Okay, keep these things in mind. These three directions and these three components, like what is u, v, w. So if you are talking about u, there's the changes in the dx. Dx is changing basically, and yeah, 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 huh, yeah. Because longitudinal, in the sense I'm telling, like the longitudes are varying actually. The variations are in the longitude. Yeah, 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 huh, huh, yeah. Dx means it is I. Yeah, huh, okay. Yeah. No, no, I'm telling the movement is along a latitude, but the variations are coming in the longitude. Like suppose I'm moving around the 0 degree latitude. So the movement is east, west to east, right? The variation, so if at this point, my latitude will be around, suppose 50. Then at this point, it is 60. Then again, it is 70. Yeah. So the variations are coming in the longitude. So I am telling I am moving along a latitude and I am having longitudinal variations. Yeah. And the other thing, meridional, I am moving along a longitude and I am having variations in the latitude. The variations are along a, like latitudinal variations I am getting. So that is dy. Clear? Yeah. I hope it is not confusing actually. Oh. So this is basically variations. I am moving along a latitude and I am having longitudinal variations. Change in longitudes is represented as dx, and then here I am having latitudinal variations. Change in latitudes are represented as dy, and altitude is just height, how it is changing along the height. I hope it is clear. Not I didn't confuse you. I hope. Okay, if you have any doubt, you can always come back. I think that discussion forum is also there. You can post your doubts over there also. If something I have said is wrong or some confusions I have created, so just post it there. I will see. I think it's fine for today. We'll stop it here. Yeah. Yeah. If you have any doubt, you can ask me, or we can. Yeah. We can. We can wind up the session. Yeah. Yeah. I'm recording. You will be able to view it actually. I think in the NPTEL site itself you can get live interactive sessions recording also they are providing. So that link, if you go, you can see. Yeah, I think some permission issues was there when I did it earlier, sharing. So I was receiving mails. I will check that from this week onwards. I have changed the previous ones also. Now I think everyone can access. So you can go through it. Yeah. Yeah, good night. Thank you. Yeah.